There is a moment on every single commercial flight, every one, where a machine weighing anywhere from 150,000 to 800,000 pounds, moving at roughly 150 miles per hour, intentionally throws itself at a concrete surface. That's landing. And when you describe it that way, it sounds less like a graceful conclusion to a flight and more like a controlled collision, because that's exactly what it is. The pilots are not gently placing the aircraft down. They are managing a controlled fall. The plane is descending at a rate of anywhere between 2 and 6 feet per second. The tires make contact with a runway that is not soft, not forgiving, and not slowing down for anything. All of that force, all of that momentum, has to go somewhere. And the place it goes is a set of mechanisms hiding underneath the fuselage that most passengers notice for about 4 seconds before ignoring for the rest of their lives. The landing gear. The wheels. You've seen them. You've heard them clunk into place on final approach. Maybe you've watched them fold up into the belly of the plane through your window right after takeoff. But here's what almost nobody thinks about. The engineering packed into those wheels and struts is some of the most sophisticated on the entire aircraft. And the way it works, the actual physics of how a commercial jet absorbs a landing without crumbling, is one of the most clever things humans have ever built. So let's look at what's actually happening right underneath your feet. This is plainly put, where we take the things you've seen 1,000 times and finally explain what's actually going on. Hit subscribe right now because we do this every Tuesday, and the best part of today's video is still ahead. Start with a number that might change how you think about landing forever. A Boeing 777-300ER on a typical long-haul flight touches down at a maximum certified landing weight of around 554,000 pounds, that is 277 tons, moving at 160 miles per hour, hitting the ground. In under 1 second, the plane goes from flying through air to sitting on pavement, and every pound of that weight, all 277 tons of it, needs to stop moving downward. The structure that handles this is called the main landing gear, and on the 777 it consists of 2 massive assemblies, one on each side of the fuselage, each supporting a bogie. That's an aviation term for the wheel truck, the cluster of wheels at the bottom of each landing gear leg. On a small regional jet, you might see 2 wheels per leg. On the 777, there are 12 main wheels in total, plus 2 on the nose gear, giving you 14 tires on the aircraft altogether. The reason for 12 wheels comes down to a problem that most passengers have never even considered: the ground. Not the runway surface itself, but the pavement underneath it. Airport runways are rated by something called pavement strength, essentially how much weight they can handle distributed over a given area before the surface starts to crack or deform. The more weight you put on fewer wheels, the more pressure each wheel pushes into the ground. Push too hard, and you start damaging the runway. So as aircraft got heavier, engineers had a choice: add more wheels or add more landing gear legs. The 777 went with more wheels per leg, 2 enormous 6-wheel bogies, spreading 277 tons across 12 contact patches instead of 4. Each individual tire on a 777-300ER's main gear carries a certified load of about 59,000 pounds. That is more than a loaded semi-truck on a single tire at over 150 miles per hour. The tires themselves are engineering marvels on their own. They are inflated to around 200 pounds per square inch, roughly 6 times the pressure in your car tires. They have to withstand not just the weight of the aircraft, but also the sudden burst of friction when they go from 0 to 160 miles per hour in the first fraction of a second of touchdown. Think about that. The wheel is just hanging there, not spinning, during the approach. The moment it touches the runway, it has to spin up from 0 to match the aircraft's ground speed almost instantaneously. The heat generated by that friction is intense enough that you can sometimes see smoke trailing from the main gear on landing. That's not the brakes, that's the tires spinning up, and yet they hold. Every time. But the tires are not really what absorbs the landing. That job belongs to something hidden inside the strut itself, the piece of engineering that makes the difference between a landing you barely notice and a landing that would shake the airframe apart. It's called an oleo strut, and it has been sitting quietly inside the landing gear of almost every commercial aircraft for over a century without most passengers ever knowing it exists. The original patent was filed by Vickers Armstrong back in 1915. The fundamental design hasn't changed that much since, because it is that good. Here is how it works. The strut is a telescoping tube, an inner cylinder that slides into an outer cylinder. The outer is connected to the airframe. The inner is connected to the wheels. Inside the lower chamber, there is hydraulic fluid oil. Inside the upper chamber, there is nitrogen gas under pressure. The two chambers are separated by a tiny hole called a metering orifice. When the wheels touch down, the sudden upward force compresses the strut. The inner cylinder pushes upward into the outer. As it does, hydraulic fluid is forced through that tiny orifice from the lower chamber into the upper one, where it compresses the nitrogen gas. Two things happen simultaneously. The nitrogen acts like a spring, absorbing the energy of the impact and storing it. The oil being forced through the tiny hole acts like a damper. It slows everything down, converting kinetic energy into heat, the way a car's shock absorber works on a bumpy road. The combination means the landing energy is not transferred into the airframe all at once. It is spread out over the full stroke of the strut, stretched over time, reduced from a violent spike to a manageable load. What this means in practical terms is remarkable. Without the oleo strut, even a smooth touchdown at 2 feet per second would transmit an enormous jolt through the wing spars, the fuselage frames, the passenger cabin. With it, what you feel as a passenger is a brief bump, usually not even that. The energy that would have cracked metal and stressed joints is instead quietly converted into a few degrees of heat inside a sealed tube of oil and nitrogen, and then it's gone. You recline your seat. You don't think about it. And the strut has one more trick. On the ground, after landing, it acts as a suspension system for taxiing. Those 12 wheels rolling over runway expansion joints, tarmac bumps, and jet blast from other aircraft, the oleo struts absorb all of that too, continuously, invisibly. The same mechanism that handles a 277-ton landing also handles the gentle rocking of pushing back from the gate. Now, here's where the landing gear goes from impressive to genuinely remarkable. It has to disappear. During flight, landing gear is a catastrophic source of drag. Imagine holding your hand out a car window at 60 miles per hour. Now imagine doing that with a structure the size of a small car, mounted on the belly of an aircraft doing 500. Leaving the gear down in flight would increase fuel consumption dramatically and reduce range significantly. So the entire assembly, the struts, the bogies, the 12 massive tires has to fold up into the belly of the aircraft in roughly 8 seconds after takeoff, close behind sealed doors, and sit there for the duration of the flight. The retraction sequence is a choreographed mechanical ballet. Hydraulic pressure at over 3,000 pounds per square inch drives actuators that rotate the landing gear, legs up and inward. The gear doors open first, then the gear swings up, then the doors close behind it, restoring the smooth aerodynamic underside of the aircraft. The whole sequence takes less time than it takes to read this sentence twice, and it has to work in the opposite direction, every single flight, reliably, or the plane can't land. There are safety systems layered into this process that reveal exactly how seriously engineers take the possibility of it going wrong. The most important one is something called the squat switch, a small electrical sensor mounted on the main gear strut. When the aircraft is on the ground and the weight of the plane compresses the strut, the squat switch opens a circuit that physically prevents the gear from retracting. It doesn't matter what the pilot does with the gear lever. It doesn't matter if there's a short circuit, a software glitch, or a confused input. If there is weight on the wheels, the gear cannot go up. This single, elegantly simple safety feature prevents one of the most catastrophic possible failure modes in aviation gear retraction while still on the ground, through a mechanical interlock that requires no computers, no software, and no pilot awareness to function. And then, if the hydraulic system fails and the gear can't extend normally on approach, gravity gets the job done. Every commercial aircraft has an emergency extension system. Hydraulic pressure is released, the uplocks disengage, and the gear falls down and locks into position under its own weight. On some aircraft, there is also a pneumatic backup, using pressurized air to push the gear down if gravity alone isn't enough. In over a century of commercial aviation, the landing gear has failed to extend on approach only a handful of times, and in most of those cases, the backup system worked. The next time you're on final approach and you hear that distinctive clunk-thunk from underneath the floor, that's the gear coming down and locking into place. The green lights on the flight deck confirming 3 green, nose gear down and locked, left main down and locked, right main down and locked. Inside those struts, 12 tires inflated to 200 pounds per square inches are spinning up to meet a runway at 160 miles per hour. Hidden inside each strut, oil is waiting to push through a metering orifice a few millimeters wide and turn 277 tons of falling momentum into a tiny puff of heat. The most violent thing that happens to every plane you've ever flown on, and you barely feel it. And that, plainly put, is what your landing gear actually does. Don't forget to subscribe to Plainly. Put every Tuesday we find something hiding in plain sight and pull it apart so you can finally see what's going on. Drop a comment below and tell us what you want us to explain next. We read every single one.